Okay, welcome back. Last time we looked at momentum in 1D, so we're going to extend that to 2 dimensions. And so we're going to have kind of the same essential questions. We're looking at when momentum is conserved, and remember we said that was when the external force on a system was 0. And we're going to be looking at collision problems in 2D. So it's actually fairly simple. You simply use conservation of momentum independently for the x and y dimensions, and you have to resolve your momentum vectors into components. Now, the last thing to point out is that you can get 2 equations from x and y dimensions for 2D collisions, but then you can also get a third equation from kinetic energy, saying that k initial is equal to k final. And so this can help if you need to find 3 unknowns. Excuse me. So here's an example of a 2D problem. Okay, so a pool player hits a cue ball in the x direction at 0.80 meters per second. So that's going to be V1 initial. The cue ball knocks into the 8 ball. Okay, so here's the 8 ball before the collision, and then it's at rest. And we're going to assume that these have the same mass m. So this is the initial picture. Then afterwards, the 8 ball is going to move off at a direction 35 degrees above the x-axis, and this is going to be a V1 final of 0.30 meters per second. And then that means that the cue is going to be going this way with, I guess that would be a V2 final, with a V1 final and an angle like this. Okay, so what we're trying to find is this angle of deflection, theta. So we really have 2 unknowns in this. Could be a lot worse. The fact that we're given the final speed of the 8 ball really helps us. So we want to use conservation of momentum, and we want to set it up like this. P initial x equals P final x. It doesn't matter if you write Px initial or P initial x, whatever makes sense to you. And then we also want to write P initial y is equal to P final y. I'll probably end up writing it both ways at some point. And we don't know if this is elastic or not, so we can't write an equation for kinetic energy. Okay, now we know that in the x direction, before the collision, we're going to have mv1 initial. Okay, the 8 ball doesn't have any momentum before the collision. Afterwards, both objects have x momentum. The cue will have m v1 final cosine theta for its momentum, and the 8 ball will have m v2 final cosine 35 degrees. We also know v2 final is 0.30. Okay, so that's going to be one equation, and whoops, notice that okay, just misbehaving for a second. The m's are going to cancel out, which is good. Okay, and also note that v1 initial is 0.80, so we really only have 2 unknowns in this equation, v1f and cosine theta. And then we also have p initial y equals p final y. Well, what is p initial y? It's 0. P final y is going to be m v1 final sine theta with a negative sign because that is downwards. And then we're going to have plus m v2 final sine 35 degrees. Okay, so here's how I would solve this. Cross these out here, and we have 2 unknowns in this equation. Okay, and we could write this as v1 final sine theta equals v2 final sine 35, or we could just write this as v1 final equals V2 final, which is 0.30 sine 35 degrees over sine theta. And you'll see why I'm doing it this way in a second. Remember that what we want is the angle of deflection. So if I can take V1 final and plug it into here, hopefully I can cancel that out and only have an expression that has the angle in it. Okay, so if I do that, I would write that as V1 initial, which is 0.80, is equal to V1 final, which we're saying is 0.30 sine 35, and then that's over sine theta times cosine theta plus 0.30 cosine 35. And now we have an easy expression to solve here. And we can do that fairly easily. We'll do 0.8 minus 0.3 times cosine of 35. And that's going to give us about 0.5543 is equal to 0.3 sine 35 over the tangent of theta, because cosine over sine is cotangent, which is 1 over tangent. So 0.3 times the sine of 35 is 0.1721. I'm rounding a little bit. And this is going to give us an angle theta here of about 17.2 degrees. Okay? And I can actually tell you that this is definitely not an elastic collision based off of this angle. Okay? And we'll actually see in the next problem what angle we need to have between these two vectors in order for it to be elastic. But this is definitely not. Okay, well, just to recap, what we did was we wrote equations for x and y momentum, and then we solved the system. Okay, so here's another example. A proton moves with a velocity of v initial I hat. It collides elastically with another proton initially at rest. Okay, so the two protons have equal speeds after the collision. We want to find the speed of each in terms of vi and the direction of the velocity of each. So here's a proton moving at v initial I hat. It's going to collide elastically with another one at rest, which means that afterwards we're going to have our two protons, and this is going to be, we'll just call it v final and v final. Okay, and we want to find the direction of the velocity, so this could be theta 1 and this could be theta 2, but I'm going to take a huge shortcut here, and because these are all the same mass, here's a little trick that I can do. Because kinetic energy is conserved when it's elastic, I can write k initial is equal to k final. So 1/2 m v initial squared is equal to 1/2 m v final squared plus 1/2 m v final squared. So I can actually solve this in terms of the velocity of each, okay? And the 1/2 m's are going to cancel out. And in order for velocity or kinetic energy to be conserved, we're going to have basically v initial squared is 2 v final squared. So v final is going to be root 2 over 2 v initial. So that's the speed. But the other thing that I wanted to show you is going back to this equation right here. This can be written as v initial squared equals v final squared of 1 plus v final squared of 2. And I'm doing this in the case where v1f and v2f don't have to be the same. Now I want you to think about the momentum. Let's think about what that looks like. The initial momentum looks like this, and the final momentum, well, one of them looks like this, and the other one looks like this. And you guessed it, this is, if this is P1 final and P2 final, It's a right triangle. And if they have the same mass, then we get a Pythagorean theorem. Now, what does that tell us about these two angles, theta 1 and theta 2? It means that theta 1 plus theta 2 has to be equal to 90 degrees for an elastic 2D collision where M1 is equal to M2. Now, is this always the case? No, but this is a pretty special case where it is. So now there's a number of ways that we can get the direction of the velocity. Probably the easiest way is just to set up momentum in the x direction, okay? And so we would say P initial x equals P final x, and that's going to lead us to mv initial plus 0, right, is equal to mv final cosine theta 1 plus mv final cosine theta 2. Now, if I wasn't using my shortcut, I would then go ahead and set up P initial y equal P final y, which would say 0 is equal to m v final sine theta 1 minus m v final sine theta 2. And those are all the same. And by the way, this tells me, since the VFs and the M's are the same, this tells me that sine of theta 1 is equal to sine of theta 2, which also leads me to the fact that theta 1 is equal to theta 2. So there's just so many ways to go about doing this. And so I cross these M's out here, and I'll get VI is equal to VF, which is root 2 over 2 VI cosine of theta. And then VF is going to be root 2 over 2 VI cosine of theta. Okay, so why am I writing it like this? Well, the VI's cancel, and I'm going to get 1 is equal to 2 root 2 over 2 cosine theta, which is just root 2 cosine theta, or cosine theta is equal to root 2 over 2, which means that after all is said and done, theta is 45 degrees. So that's kind of cute, okay? Now, often you're going to get a problem where the angles aren't the same, but remember that we have basically 3 equations to bring to bear on this to deal with up to 3 variables. Okay, so V1F, V2F, and perhaps one of the angles. If we have more than that that's unknown, then we're not going to be able to solve it. Okay. Okay, so next time we'll talk about center of mass.